Hi guys, I'm Mr. Joseph, your chemistry teacher. I'm back with my lectures. And today's lecture we'll be looking at Gibbs free energy change. And our lesson objectives are, at the end of the lesson, I think students should be able to state and use the Gibbs equation. Then also carry out calculations using the equation. Then we can also state that the reaction or process will be feasible by using the sign of what the Gibbs free energy change. Then predict the effect of temperature change on the feasibility of a reaction, giving standard enthalpy and the entropy changes. So please, I want us to pay attention to this lecture and get the best out of this lecture. It's a continuation of our previous lecture on enthalpy changes in reaction. So we want to look at the free energy change using Gibbs free energy change. So please listen attentively and get it. So we are looking at Gibbs free energy. Gibbs free energy is named after an American scientist, Josiah Willard Gibbs, who applied the concept of entropy and applied energy changes to chemical reaction and physical process. Now, on a general ground, chemists are usually interested in the system of reactants and products, rather than having to consider the energy changes with the surrounding. We all know that during chemical reaction, heat is either released from the system to the surrounding or from the surrounding to the water system. But chemists are usually interested in the system of reactant and product rather than what is happening in the surrounding, rather than what is happening in the environment. Fortunately for us, there is a way in which we can take account of both the system and surroundings in a more straightforward way, which involves a quantity called Gibbs free energy, or more simply free energy. So it can also be called what Gibbs free energy or Gibbs function. So it takes into consideration what happened within the system and also the surrounding. Now, what is Gibbs free energy? In fact, what is free energy in general? When we talk about free energy, the free energy is the amount of energy that is available for useful work. When energy is applied to a system, the amount of energy that is converted into useful work is what we call free energy or Gibbs free energy. Now, the quantity of Gibbs free energy is used to determine whether a chemical reaction is likely to be spontaneous or not, whether a chemical reaction is feasible or whether a chemical reaction is not feasible. If we want to talk about the Gibbs free energy, it has to do with the enthalpy of the reaction, the entropy. So what the free energy of a chemical system G is that energy which is available for doing work. So this is the driving force that brings about a chemical change. Yeah, the driving force that brings about a chemical change. It's a factor, in fact, that helps us to determine whether a reaction is likely to occur or whether a reaction is not likely to occur. We talk about total entropy, which is the entropy of the system plus the entropy of the surrounding. So the Gibbs free energy brings the entropy of the system and the entropy of the surrounding. It puts into consideration the entropy of the system and also entropy of the surrounding. So we'll talk about total entropy, which is entropy of the system plus entropy of the surrounding. The entropy of the total entropy will now be entropy of the system minus enthalpy of reaction divided by temperature. So if you multiplying through by T, you get what? You get the total entropy, T delta S, which is the D delta S total, is equal to T delta S system minus what? Enthalpy change of the reaction. So what happened that if you rearrange, you get minus T delta S total will be equal to what? Minus T delta S system plus the enthalpy of the reaction. So the quantity is minus T delta S is called what? The Gibbs free energy change, which is the free energy change. So D minus T delta S is equal to what? Delta G. So that means delta G, which is the free energy, will be equal to what? Minus T delta S plus what? Enthalpy change of reaction. So it can be written as delta G now equal to what? Delta H minus what? T delta what? S. So this is the free energy, this is the enthalpy of the reaction, this is the temperature, and this is what? The entropy of the system. So free energy, which is delta G, change in free energy is equal to the enthalpy change of the reaction minus temperature times what? Entropy change of the entropy of the system, change in entropy of what? The system. So it's as simple as what? ABC. So we've established the fact that delta G is equal to minus T delta S, delta G delta G is equal to minus T delta S total, which is the total entropy. So, and minus T delta S total is equal to minus T delta S system plus enthalpy change of the reaction. Enthalpy change of the reaction. So that means delta G now will be equal to minus T delta S system plus enthalpy change of the reaction. So if we are to rearrange this, we'll now have delta G will be equal to what? Delta H, reaction enthalpy change of the reaction, minus what? T delta S what? System. So the expression gives us the relationship between the free energy, enthalpy change of reaction, and entropy change of the system, whereby T is the temperature. So we can calculate the Gibbs free energy change. We can calculate what the Gibbs free energy change for a reaction if we know the entropy change of the system, which is in joule per Kelvin per mole, the enthalpy change of the reaction, which is in kilojoule per mole, of which we have to convert it to joule per mole. Then if we know the temperature, which is in Kelvin, we are using under standard condition, the temperature should be what? 298 Kelvin, which is 25 degrees Celsius. So once we know these values, we should be able to calculate the free energy change of the reaction. Now the Gibbs free energy change, with the help of the Gibbs free energy change, we can tell if a reaction is spontaneous or not spontaneous. If a reaction is likely to occur or it's not likely to occur, that means if a reaction is feasible, if it's not feasible. So we're looking at Gibbs free energy change and spontaneous reaction. So with the value of the Gibbs free energy change, if the Gibbs free energy change is less than 0, the reaction is said to be what? Spontaneous. But if the Gibbs free energy change is greater than 0, which is the Gibbs free energy change is positive, the reaction is said to be non-spontaneous. The Gibbs free energy change is equal to 0, the reaction is in a state of what? Equilibrium. So a reaction is likely to occur if the Gibbs free energy change is negative. So in any reaction, we need to consider what we have to do to make what? The Gibbs free energy change negative, so that the reaction is likely to occur. The reaction is only spontaneous when the free energy change is negative, that is greater than 0. Once the free energy change is positive, the reaction is non-spontaneous, it's not likely to occur. So we're looking at still on Gibbs free energy and spontaneous reaction. Free energy, enthalpy, and entropy are related by the formula delta G is equal to delta H minus T delta S system. We've established the fact that a reaction should be spontaneous if the free energy is negative. A reaction is likely to occur if delta G, which is the free energy, is negative. So whenever we are given a reaction, whenever we are given a system, so what we have to look at the reaction, whether it is an endothermic reaction or it is an exothermic reaction. If the reaction is exothermic, then that means the value of the enthalpy change of the reaction will be negative. But if the reaction is endothermic, the value of the enthalpy change of the reaction will be positive. The next thing we have to consider is the entropy change of the system. If there's an increase in disorder, that means the entropy change is positive. If there's a decrease in disorder, that means the entropy change is negative. Then next thing we need to consider is the temperature. Is the temperature high or low? It can affect T delta S. It can affect the entropy of the system. So if the temperature is high or low, we have to put that into consideration. So generally, if the enthalpy in the reaction is negative and the entropy change is positive, then the free energy must be negative. That means the reaction is likely to occur. But if the enthalpy of the reaction is positive and the entropy change is negative, then the free energy must be positive. That means the reaction is not spontaneous. The reaction is not likely to occur. So we need to consider other factors that have to be put into place for delta G to become negative. Like temperature, we might increase the temperature, or maybe we'll decide to have a high value of the entropy change of the system. So we have to look at other things we need to do to make the reaction feasible, so that delta G will become negative, so that the reaction is likely to occur, so that the reaction becomes spontaneous. So this is a typical example reaction of hydrogen with fluorine to give you hydrogen fluoride. If you look at the reaction, the enthalpy change of the reaction is negative because this is a highly exothermic process. Then if you look at the entropy, we have equal number of moles on the reactant and the product. So the entropy change is 0, so the same number of gas molecules. So the automatically delta G, which is the free energy, becomes what? Negative. Delta G must be negative because you are taking 0 away from a negative number. So the reaction is likely to occur. The reaction is feasible. So these are the things we have to consider before what? We have to consider when giving a reaction to tell if the reaction is likely to occur or if the reaction is not likely to occur. So the free energy is negative, the reaction is spontaneous, it is feasible. So this is another example before us. So this formation of an ionic solid from this gaseous ion, which is lattice energy. So automatically the enthalpy of the reaction is negative, it's highly exothermic reaction. Then if you look at the entropy change is negative. There is decrease in the degree of disorderliness or randomness. You are moving from what? Gas towards solid. So more order in the solid. So the entropy change is negative. So delta G becomes what? Negative due to the high value of the lattice enthalpy, which is lattice energy. Lattice energy is highly exothermic. So the reaction is feasible. It's an exothermic process. So the reaction is a highly exothermic process. So delta G is negative. So the reaction is spontaneous. The reaction is likely to occur. So before us is another example. If you look at the equation, it's thermal decomposition of ammonium nitrate to give you ammonium ion and nitrate ion. So if you look at the equation, it's an endothermic process because it's decomposition. So delta H, enthalpy change of the reaction is positive. So the reaction is an endothermic reaction. Then if you look at the equation, it describes that there's a change from what solid to what aqueous state. Aqueous. So the entropy change is positive. There's an increase in entropy. So more disorder, the lattice break up. So there's an increase in entropy. That means the entropy change is positive. So that means the free energy, if we are to apply it, the free energy will become what? Positive. Delta G will become positive. So the reaction is said to be what? Non-spontaneous. So for us to make the reaction spontaneous, we'll either increase the temperature, we use a high temperature, or the value of entropy change is big enough. So that is the only way. So delta G to be negative. So for the reaction to be spontaneous, for delta G to be negative, this reaction can only be spontaneous by an increase in temperature, or if the value of delta G is big enough. So this is a task before us. Please, I'm leaving this task with us. I want us to attempt this task based on the previous examples we've treated. What is the sign of the entropy change in the following reaction? Give reason for your decision. And what is the sign of the delta G, which is the free energy? So it's as simple as ABC. Just pay attention to what we've treated in the past, and I believe you should go to do that. Here again is another task for us to handle. What is the sign of the entropy change in the following reaction? Give reason for your decision. And what is the sign of the free energy, which is delta G? So look at the equation, look at the reaction, and consider the factors, the enthalpy change, the entropy change, and give the sign of the entropy change, the sign of the enthalpy change, and say whether the reaction is spontaneous or non-spontaneous. It's as simple as ABC. So I want us to attempt as many questions as possible and get back to me if you encounter any difficulty. I'm always there for you. I'll be there to attend to you. So this is the next question for us to handle again. What is the sign of the entropy change in the following reactions? Give reasons for your decision. So this enthalpy change of atomization of sodium. So as you can see, so you have to consider the enthalpy change. You have to consider the entropy change, whether there's a decrease or increase in entropy. And then you tell if the reaction is spontaneous or not with the sign of what? The free energy. So please attempt this and solve as many questions as possible. And feel free to reach out to me if you encounter any difficulty. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. So feel free, attempt the questions. So to calculate the free energy, Gibbs free energy calculations, calculating Gibbs free energy, we use the expression free energy is equal to enthalpy of reaction minus temperature times the entropy of the system. So the entropy change of the system is in joule per Kelvin per mole. The enthalpy change of the system is in joule per mole. So we have to multiply the value of the enthalpy by 1000 because the entropy change is in joule per Kelvin per mole. Then our temperature must be in Kelvin, but since we are using standard temperature, it will be 298 Kelvin. So these are the things we need to put into consideration while trying to solve calculation of the free energy, which is Gibbs free energy. We're trying to calculate Gibbs free energy. So this is a typical example. This is a solved example for us to see. You are asked to calculate the Gibbs free energy change for the decomposition of zinc carbonate at 1200 Kelvin. So this is the temperature. The temperature has been given to us. Then we are given the enthalpy change of the reaction, which is 71.0 kilojoule per mole. So what happened? We are to calculate the Gibbs free energy. Then if you look at, we are given the entropy of the system, which is 174.8 joule per Kelvin per mole. The enthalpy change of the reaction. So we are to calculate for the Gibbs free energy. So to calculate the Gibbs free energy, standard Gibbs free energy is equal to enthalpy of reaction minus the temperature times what? The entropy of the system. So enthalpy of reaction is 71.0 kilojoule per mole. We'll convert it to joule per mole by multiplying by 1000. So we'll have 71,000 joule per mole minus the temperature. The temperature is 1200 Kelvin times the entropy of the system, which is 1 plus 174.8. So if we are to calculate 7,100 minus 209,760. So the Gibbs free energy is equal to minus 139 kilojoule per watt per mole. So as the value of the free energy is negative, the reaction is spontaneous at 1200 Kelvin. So the sign indicates that the reaction is spontaneous, the reaction is feasible, and the reaction is likely to occur. So as you can see, it's as simple as ABC. All you need to do is just get the values and represent them in the equation, which is delta G is equal to delta A minus T delta S. So it's as simple as ABC. So the question before us is a typical examination question. It's an exam style question, so please, I want you to listen attentively as you solve this question. Barium hydroxide reacts readily with ammonium chloride on mixing at room temperature. You can see the reactant and the product, and we are given the enthalpy change of the reaction, which is 133 kilojoule per mole. Some relevant standard entropies are given in table 1.2. You can see the table. You can see the entropies of the product and that of the reactant. So you are asked to calculate the standard Gibbs free energy change for this reaction at 25 degrees Celsius. So the first thing we need to do, we have to write the enthalpy of the reaction. Enthalpy of the reaction. Enthalpy of the reaction, which is in kilojoule per mole. We have to convert it to what? Joule per mole. You multiply by 1000. So you have 133,000 joule per mole as the entropy of the reaction. Enthalpy of the reaction. Then the temperature, you convert it to Kelvin, which is 25 plus what? 273. So you have what? 298 Kelvin. Then the entropy of the system will be equal to what? The entropy of the product minus what? The entropy of the reactant. Now let's see, entropy of the product. The product will be equal to 2 times the entropy for ammonia, which is 192, plus that of barium chloride, which is 203, plus 8 times 70, which is 8 moles of water. So it will now be what? 384. 2 times 190 is 384, plus 203, plus 8 times 70, which is 560. So by the time you add it, you have 1147 joule per Kelvin per mole. Per Kelvin per mole, which is the entropy of the product. Now, to calculate the entropy of the reactant, I have to erase this so that I will have enough space. The entropy of the reactant will be equal to 427, which is for barium hydroxide. 427 plus 2 times 95, 2 moles of ammonium chloride, 95, so will be equal to 427 plus 190, 190, which is equal to 617, which is the entropy of the reactant. So I have to erase for space. So we can now calculate the entropy of the system. So to calculate the entropy of the system, will be equal to entropy of the product minus that of the reactant, which is 1147 minus 617, 617. So you have 530 joule per watt, joule per Kelvin per mole. So that is the entropy of the system. So we are to calculate what? We are to calculate the standard Gibbs free energy. Standard Gibbs free energy delta G is equal to what? Delta H minus T, entropy of the system. So the free energy will be equal to enthalpy of the reaction is 133,000 minus temperature is 298 times entropy of the system, which is 530. So it will be 133,000 minus 298 times 530, which is 157,940. So the standard Gibbs free energy change is 133,000 minus 157,940 will be equal to minus 24,940 joule per mole. So it's in kilojoule per mole. So all we have to do is to divide by 1,000 to convert it to what? Kilojoule per mole. This is joule per mole. So just divide by 1,000. So by the time you divide by 1,000, let me erase the top so that I can put the answer here. So divide by 1,000. So the Gibbs free energy change. So the Gibbs free energy change will be equal to minus 24.94 kilojoule per mole. Just divide by 1,000. So you have kilojoule per mole. So you can see that the standard Gibbs free energy change is minus 24.94 kilojoule per mole, which is an indication that the reaction was spontaneous, because the Gibbs free energy change is negative. So the reaction is spontaneous, the reaction is feasible, it is likely to work. So as you can see, it's as simple as ABC. All you just need to do is to do the normal conversion and apply the formula, and it's as simple as ABC. So please solve as many questions as possible, and feel free to reach out to me if you encounter any difficulty. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. So feel free to reach out to me in case you encounter any difficulty. Thank you very much for listening. Please don't forget to subscribe to my YouTube channel. Don't forget to like. Don't forget to share. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. Thank you very much. I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel. Thank you for listening. Please subscribe to my YouTube channel, like, share. I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel, Mr. Joe, your chemistry teacher.